Hi, I'm Connors McMiniman.
I'm Mitchell Seamantle.
And I'm Brian Buckles, and our project is the optical touchscreen attachment.
For a project outline, we're going to start with project motivation, which is why we chose this project. Next, we'll discuss project description. This is how we intend our project to work and what we want it to look like. Next, we'll discuss the engineering requirements. These are the requirements that define our scope and the specific specifications we would like our project to meet. This is then followed by a black box diagram, which explains from a very high level the inputs and outputs of our overall system. This is then followed by a top level block diagram, which is slightly more detailed and it explains each block individually instead of the whole project as a whole. And finally, we'll talk about our future work, which is an overall timeline of where we intend to be throughout the rest of the term.
I will begin by providing the motivation for this project and why it is relevant in today's market. Popular touch interfaces first came to the market in the mid-90s on many smaller cell phones. In the early 2000s, the market saw a boom in the popularity of touch-capable devices with Apple's introduction of the iTouch. Even handheld gaming devices, such as the Nintendo DS and PlayStation PSP, made the transition. From there, the evolution quickened. Edition after edition of Blackberries, iPhones, Galaxies, and countless other touch-friendly smartphones hit the market. Multimedia tablets, reading tablets, and gaming tablets came shortly after. Even today, the evolution continues as corporations introduce new touch-capable laptops and desktop PCs. Ever so slowly, mechanical buttons are being eliminated to make room for larger, touch-capable devices.
Along with recent hardware advances, software has been emerging. Google's Android OS and Apple's iOS both rely heavily upon the touch interface. The Galaxy S3 phone, iPad, and iPhone would not be where they are today without the touchscreen interface to fully unlock their potential. On October 26th, Microsoft released Windows 8. This brings a whole new market to the touchscreen interface. The desktop market will add millions of new touch-oriented devices.
The concern is not only over home desktop use. What about places like these? Dearborn and the library. It would cost thousands of dollars to upgrade every monitor on campus. Next, we will talk about the project description and how we plan on allowing older monitors to offer the touchscreen interface of the future at a lower cost.
Our project can be defined as a scalable attachment that enables touchscreen capabilities on pre-existing monitors using optical touchscreen technology. Our project can be broken up into three sections. The first section is the attachment method. Our attachment needs to be scalable so that it can fit on many different types of monitor shapes and sizes. The attachment will harness the cameras. The cameras that we'll use are very small CMOS cameras. They need to be placed in the corners of the monitor. This allows them to have the best view of the screen. The next section is touchscreen technology. We decided to use optical touchscreen technology. This uses the cameras to create an optical field that the user can then break with his finger, and that will create a shadow. The shadow is then caught on the cameras and that video feed is sent to the microcontroller. The microcontroller then processes the video feed and turns it into data we can use. Lastly, we have the code section. In this section, an algorithm takes the camera data to locate the origin of the shadow. Once we have this, we know where the touch took place. With this, we can take that location and initiate a click or swipe on the computer. This then makes it touchscreen capable.
We will next talk about the engineering requirements. The idea behind our first requirement is that we want the device to be easy to use, set up, and maintain. If the product is frustrating to use and set up, the device will lose much of its value. The next highlighted requirement is to highlight the fact that this is an alternative for buying a new monitor. Large touchscreen monitors are expensive, and buying an attachment instead of a monitor should lower the total cost to the user.
Furthermore, the device should fit with pre-existing hardware. It should be scalable to fit monitors from 17 to 35 inches, as well as fit properly with the majority of monitors. The idea is to have the consumer buy one product knowing it will fit their monitor at home. The device should also be aesthetically pleasing. In order for the device to be marketable, the consumer needs to like the look and feel of the product.
The device needs to consume minimal power. Therefore, the device will only be powered from the USB. For obvious reasons, the device needs to operate in typical home environments. This means that the device will be operational in both light and dark environments and work at room temperature.
Most importantly, we want the device to operate in an accurate and intuitive manner. In order to make this happen, the device should acknowledge 20 touch locations per second, as well as report a touch location within 5 millimeters of the actual touch point. Nothing is more frustrating than an improperly working touch device, and we hope to avoid this frustration entirely. Furthermore, in order to prevent damage to pre-existing monitors, touches should be detected with less than 25 newtons of force.
Our last set of engineering requirements aims to help the device withstand typical wear and tear. We understand monitors are often moved and/or bumped. If the cameras do not remain exactly in place relative to the monitor, these movements could throw off calibration enough to frustrate the consumer. Because our goal is to provide an intuitive and stress-free touch experience, we intend to build an attachment method secure enough to withstand slight movements. On the other hand, we also intend on leaving no damage to pre-existing monitors. So while the attachment needs to be very tight and secure, it must also leave little to no residue, scuffs, or marks on the screen.
Next, I will go over the top-level black box diagram. As you can see, we have 3 inputs and 1 output. The 3 inputs we have are the touch input, device power, and outside environment. The touch input is a shadow cast by the finger or pointer onto the touch point. The second input is the device power. The device is powered by USB, which runs at 5 volts plus or minus 1/4 of a volt, and a current of 500 milliamps. Other factors that may interfere with our device and thus need to be accounted for are room lighting, temperature, and humidity. The biggest environmental factor will be the lighting, which may interfere with touches and either cause false touches or cause actual touches to be missed. On the back end of our device is the touch location control signal, which will give the computer the necessary data to calculate a touch input.
This brings us to the top-level block diagram. The camera modules, as stated before, contain CMOS cameras that output video feed. As for the interface definitions, the camera power is power supplied by the USB with a voltage of 2.8 volts and a current of 40 milliamps. The camera control signal is an I2C interface with a signal high of 2 to 2.8 volts, signal low of 0 to 0.3 volts. The camera data in is a control signal that is compiled information from all present cameras. It is also an I2C interface with a signal high of 2 volts to 2.8 volts and a signal low of 0 to 0.3 volts.
The data from the camera modules will be sent to the USB hub. Here, we need interfacing to compile data from both cameras and deliver it smoothly to the microcontroller using I2C interface. This block will also contain a voltage level shifter to shift high signals from 2.8 to 5 volts.
The microcontroller code will be written in C. It will process and filter the camera data and convert it to data to be transmitted over USB with all the unnecessary information stripped out. The filtered data will then be used by the auto location algorithm block to calculate the touch location. The calibration interface will interact with the filter code to ensure that the calculated touches are accurate.
Our project timeline begins with obtaining hardware by November 19th. This includes obtaining all the cameras, microcontrollers, and miscellaneous components that are needed for our project. Next, we will complete the lowest level block diagram by November 26th. This involves finishing schematics and interface definitions. After this, we will hope to complete the design by December 3rd. This is verification and documentation that is necessary for the course. Next, we will complete prototyping by January 7th. This will be our final block testing and construction and verifying that everything works. Finally, we will improve, finalize, and validate our design during winter term.
Lastly, we'd like to thank you for listening. I'm Connors McMiniman.
I'm Mitchell Seamantle.
And I'm Brian Buckles. Have a nice day.